Differentiation, lecture number 3, implicit functions. Let's see how to differentiate implicit functions. Suppose we are given x minus y equal to 3 and we have to differentiate it with respect to x. Then we put d upon dx before each term and we differentiate, and finally we find dy by dx. So let's differentiate it with respect to x. D upon dx, x minus d upon dx of y equal to d upon dx of 3. So this will become 1, this will become dy by dx, and this will become 0. Hence, dy by dx equal to 1. Let's consider next question. Suppose we are given x plus sin y equal to cos x. So again, we put d upon dx before each term, or we can write differentiating with respect to x. So here I'm writing differentiating with respect to x. So this will become 1. This will become cos y d by dx. This will become minus sin x. The basic rule is there. If function is in terms of y, then we write f dash y followed by d by dx. Example, d upon dx sin y. So it becomes cos y times d by dx. Another example, d upon dx of, suppose it is y square, so it will become 2y, then dy by dx. The same is true here. This is sin y, so it has become cos y followed by dy by dx. And our purpose is to get dy by dx. So we take this 1 to RHS. So cos y dy by dx becomes minus sin x minus 1, or minus 1 plus sin x. So dy by dx will be equal to minus 1 plus sin x divided by cos y. Now, next question. Suppose we are given 2x plus 3y equal to sin x. So we can differentiate with respect to x. So differentiating with respect to x. So this will become 2 and this will become 3. Then dy by dx equal to cos x. This 2 can be shifted to RHS. So 3 dy by dx equal to cos x minus 2, or dy by dx will be equal to cos x minus 2 divided by 3. Next example, suppose we are given 2x plus 3y equal to sin y. If we differentiate with respect to x, so differentiating with respect to x, so this will become 2, this will become 3, but dy by dx will appear because this function of y, or y itself, this is also function of y, so it will become cos y times dy by dx. Our purpose is to get dy by dx. So dy by dx, we can shift this term to LHS and 2 to RHS, or we can shift this term to RHS and keeping 2 in LHS, so 2, and then dy by dx can be taken common. So cos y minus 3, from where dy by dx will be equal to 2 upon cos y minus 3. Next example, suppose we have ax plus by square equal to cos y. Differentiating with respect to x. So ax will give a and by square will become 2by dy by dx, and cos y will become minus sin y dy by dx. Now we can shift this to be by dy by dx to RHS. So a equal to dy by dx common with a negative sign because this will also become minus, and then sine y plus 2by or dy by dx equal to minus a divided by sine y plus 2by. Let's take some more examples. Suppose we are given xy plus y square equal to tan x plus y. Now differentiating with respect to x. Here it is product of two functions. If you remember, d upon dx of a, b. If there are two functions, in that case, first and then derivative of second plus second derivative of first. So that will be applied here. So x dy by dx plus y, then dx by dx, that is 1, so I'm not writing, plus this will become 2 by dy by dx equal to tan x will become sec square x and y will become dy by dx. Our concern is to get dy by dx. So all terms that contain dy by dx we can put together. So dy by dx, then here x is common, here 2 by, and here it will become minus 1 when we shift it to LHS, and then sec square x, and this term will be y. So dy by dx will be equal to sec square x minus y divided by x plus 2y minus 1. Now let's take next question. Suppose we have x square plus xy plus y square equal to 50. So again, we can differentiate. Here we can apply product rule. So differentiating with respect to x. So it will become 2x. It will become x dy by dx plus y times 1 plus 2 by dy by dx equal to 0. So we can shift these two terms to RHS, or we can shift the terms containing dy by dx to RHS. Anything can be done. So 2x plus y equal to, suppose we shift these terms to RHS, minus x plus 2y times dy by dx. So dy by dx will be equal to 2x plus y divided by x plus 2y. Next question. Suppose we are given sine square y plus cos xy equal to k. So if you remember, I told you d upon dx of cos block or cos function. We can do it as cos block. So cos block gives minus sine block times d upon dx of block. So here that rule we can apply. So this will become, also we know d upon dx of sine power nx will become n sine n minus 1x into d upon dx of sine x, that is cos x. So we can apply that rule here. It will become 2 sine y into differentiation of sine y, that will be cos y, and since it is function of y, so we have to write dy by dx plus cos will give minus sine xy times d upon dx of d upon dx of xy, and d upon dx of k, which is constant, is 0. Now here we apply product rule. And 2 sine y cos y equal to sine 2y. Sine 2y dy by dx minus sine xy times x, here product rule, x dy by dx plus y times 1 equal to 0. We open the bracket. So sine 2y dy by dx minus x sine xy dy by dx minus y sine xy equal to 0. Now, this term can be taken to RHS, and here dy by dx can be taken common. So dy by dx common, sine 2y minus x sine xy equal to y sine xy, or dy by dx equal to y sine xy divided by this thing, sine 2y minus x sine xy, which is our answer. Thank you for watching.